Thank you very much for your introduction. And I'd like to say thank you for Professor Takagi and Professor Ogawa to have opportunity to speak today. So I'd like to talk about this title, Elucidation of CFRP Lightning Damage Mechanism and Damage Suppression with Conductive Polymers. So this is not a lecture or research paper. I think this is just an overview of the research activity in JAXA. So please listen my talk in a relax. So first of all, I'd like to start from the background of this work. But in the first presentation, Dr. Saotome gave us a very good lecture about lightning problems for the aircraft and the composite materials. So I think I don't have to say too much about that. So basically, as explained in the first presentation, the lightning incident in the aircraft is not a special thing. So once in 1,000 or 20,000 flight hours, every aircraft have a lightning incident. So the secure design for the lightning is indispensable for the commercial aircraft. So the recent years, the composite material is widely adapted to the commercial aircraft because of their superior mechanical properties. But basically, they have inferior electrical or thermal properties. So once the lightning current is attached to the composite structures, and the damage is relatively large compared with metallic materials if the appropriate protection is applied to the composite surfaces. So, and this affects to the inspection and the repair cost when the lightning strike attached for the airliners. And also, this phenomenon is really complicated, so difficult to understand. So the detailed damage mechanism are yet to be elucidated well. So when we want to develop the composite aircraft, the many lightning tests are required, which result in the increasing of the development cost in the type certification process. So, and in this slide, I'd like to talk about the lightning damage mechanisms. So the composite lightning damage is finished in a very short time. So every event occurs in up to the several hundred microseconds. And basically, the quite complex multi-physics problem, which involving superposed thermal, electrical, and kinetic phenomena, such as the dual heating, the electric breakdown of the matrix, and the magnetic force and acoustic force, and the temperature dependent of material, and so on. So, and the details of the effect of each phenomenon on the lightning damage and their interaction have not been clarified. So in this problem, our research approach is basically these two. We have these two approaches. The first one is to elucidation of the lightning damage mechanism of CFRP here. And second one is a developing of the new material system for the lightning protections. So the first one is lightning testing for deconstructing the physical phenomena. And also we'd like to develop multi-physics numerical simulation code to enable the virtual testing, which result in the reduced aircraft development cost. And the second one, our approach is the conductive polymer CFRP. which can reduce lightning damage and which resulting in the reducing the aircraft operation cost. Yeah. So this is my today's topic. I'd like to start from this first one. So first of all, I'd like to show you the lightning test. So the overall of the lightning testing standard is already explained in the first presentation. But in case of the lightning test for the composite panels, this kind of impulse generator is used, very big one. This is owned by the Nagoya University in Japan. So the basic way to lightning test is standardized in the SAE document, and the waveform is here, which is composed of the 4 types of waveforms, component A, B, C, and D. And the maximum current is appear in this component A and up to 200 kiloamperes. So this is the basic testing setups for the laminate. So here is the electrode, and here is the specimen, and the specimen are connected to the ground. And basically, the lightning current is applied as an arc entry. So here is the VTR of the lightning testing for the composite panels. So this is non-protected laminate without any metal mesh or coatings. But the surface is the aircraft painting applied. So as you can see, the event is finished in a very short time, maybe the 1 frame or second frame into the 1 frame or second frames. And after the lightning current applied, there's a big damage on the laminate like this. So in order to understand what is happening during the lightning damages, the high-speed camera is one of the good way to visualize the phenomena. So in this case, high-speed camera is utilized to understand the how arc route develops during the lightning current attachment. So this is used for the define the boundary condition of the impulse current when we apply to the numerical simulations. So this figure shows the testing setup. Here is the laminate here, and here is the electrode, and we use the 2 different high-speed cameras from the different directions. The one is from the line to the fiber direction, surface fiber direction, and another is aligned to the transverse direction of the surface fiber direction. So this is the result of the high-speed imagings for the transverse directions. So we can see how the arc route increase time dependency. So next video shows the fiber directions. As you can see, clearly the propagation is different between the fiber direction and the transverse directions. So this is really interesting because the transverse direction usually have a much lower electrical conductivity, but the arc route developed in the transverse directions like this. But in the fiber direction, the arc route is more concentrated. So these arc route development information will take into account to the numerical simulations. And also, the non-destructive testing is one of the good way to understand the damage behaviors. So this is the example of the after lightning test specimen here. And you can see the surface damage, including the fiber damage like this. And this is the ultrasonic C-scan images that you can see the more larger delamination occurs in the inside of the laminate like this. So when we study the relationship between the applied lightning current energy level and the detected delamination area, this graph shows the relationship between them. So with increase of the applied lightning energies, the resultant damage area will increase like this. So here, a different plot, colored plot shows the different waveforms. So this means the different shockwave effect or different waveform effect do not affect the resultant damage size, but the lightning current energy have the most important kilo here. So that from this result, we can understand the joule heat is a major factor in the lightning damages when we do not apply the surface lightning protections. So based on these knowledges, we developed the numerical simulations based on the copper thermal electric analysis here. So this is based on the finite element method. And we use commercially available FM code abacus here. So this analysis code is consists of the two different parts. The first one is the copper thermal electric analysis, and the duration is from 0 to 260 microseconds. This means the impulse current finishes in this period. And after that, the heat transfer analysis are performed to evaluate the heat transfer after the lightning test. And of course, the lightning accurate propagation is taken into account for the boundary conditions. The first electric potential is analyzed, and after that, joule heat generation is calculated, and then the thermal analysis and performed, and we can get a temperature distribution of the specimens. And then we calculate the degree of pyrolysis of the matrix regions, and this process is repeated during this impulse current. After that, the thermal analysis is performed up to the 10 seconds, and we calculate the degree of pyrolysis of matrix regions up to the 10 seconds here. And this figure shows the result of the numerical analysis, and the right-hand side shows the result of the ultrasonic C-scans obtained in the experiments. So as you can see, the overall shapes and the area shows a good agreement with each others. So in this case, in plane directions, error in the numerical simulation and the experiment is about 11%. But still, we can see the large difference in the thickness directions. So in the actual damages, more deeper delamination can be observed. So this shows we have to modify these numerical simulations more. So one of the reasons of this error in the thickness direction is it is considered that we have to take into account other phenomena such as kinetic effect. So in order to understand the kinetic effect, we try to visualize the shock wave propagation by using the Schleiden photography method. So Schleiden photography method is a well-known method to visualize the shock wave or density of the atmosphere by using this pair of Schleiden mirrors here, and high-speed cameras and laser source, light source. Here is a test specimen here. And this is a result of the example of the result of Schleiden photography. In this case, the component A, 20 kiloamperes current is applied. Oh, sorry. So as you can see, we can clearly see the shock front associated with the lightning current like this. And also, not only the shock waves, we can see the damage behavior inside of the arclet here. So basically, the lightning current associated with a very intense light, so it is difficult to see what is happening inside of the arclet. But using this Schleiden photography, we can observe of the damage behaviors like this. So another trial is to identify the pressure because of the lightning current. So we use digital image correlation techniques, which is a kind of stereography with high-speed cameras. So this is a testing setup here. Sorry. Yeah. So here is the specimen, and here is the electrode, and we observe the diffraction from the opposite side of the lightning attached side by using the two different high-speed cameras like this. And this is a result of the DAC analysis. By using this method, we can measure the diffraction history of the specimen like this. So far, we successfully measured the diffraction due to the pressure associated with the lightning current. And in the next step, we'd like to do the identification of the pressure distribution and the waveforms. And in the future, we'd like to incorporate into the lightning strike damage analysis. Yeah. Okay. I'd like to move to the next topic of the development of the new material system for the lightning protections. So based on the understanding of the mechanism of the lightning damages, anyhow, if we can improve the electrical conductivity of the composite materials, maybe we can reduce the damage by the lightning strikes. So, of course, a straightforward way, the protection mesh or metal coating is more stronger. But when we apply such kind of protections, it is difficult to perfectly prevent the lightning damages because the lightning current have huge energies. So that if the composite itself have more strong resistance against the lightning damages, maybe we can reduce the lightning damages overall. So our approach is developing the intrinsic conductive polymer by using the polyaniline here. The basic approach to improve the conductivity of the composite material is mixing the nanofiller inside of the matrix like this. But in this way, it is difficult to increase the amount of fillers because of the viscosity is easily increased when we want to mix the more amount of fillers. So in our approach, there is good point is that there is no weight increase, and the manufacturability is also good. So this is this slide shows how to how to make a conductive polymer composite. The first, every materials are mixing, the physical mixing, the polyaniline, DBSA, and DBV, and it come to the paste like this, and it is have a property of the good dispersion to the carbon fibers, so we can make the prepreg. And after that, we apply the heat and the pressure. In this case, we use the hot press process, and then the doping and the curing occurred simultaneously, because here DBSA act as the dopant and the curing agent for both ways. And then we can get a electrically conductive matrix composite like this. So in this in this research, we apply a carbon fabric with a plain woven type, and we compare the newly developed PANI, DBV, conductive polymers, and epoxy, general epoxy resins. So first, we evaluate the electrical conductivity. So we use the LCR method to avoid to avoid the effect of the contact resistance. We use the FOPO method here. And this table shows the result of the measured electrical conductivity. So as you can see, the newly developed CFPANI conductive polymer composite shows 6 times higher electrical conductivity in the in-plane direction, and 27 times higher out of plane directions. Then we evaluate the lightning damage resistance of both materials with this setup. In this case, the 40 kiloamperes and the 100 kiloamperes component A waveform is applied. So this video shows the result of that, and left side shows the result of the general epoxy composite. So once again, there's a big damage in the center of the specimen like this. And here's the result with a conductive polymer composite. So as you can see, a very slight flash occurred, and it seems there's no damage on the surface of the specimens. Sorry. So this is the specimen after lightning test. In case of the CF epoxy composite, there's a large damage on the surface. There's a fiber damage area and the resin deterioration area like this. And in case of the conductive polymer composite, there is the really slight resin deterioration area in center of the specimen like this. In case of the 100 gram pairs, the CF epoxy shows a more larger damage like this. But for the conductive polymer composite a little bit larger resin deterioration area compared with the 40 kilomperes case, but still there's no fiber damages here. And this is a comparison of the ultrasonic C-scan results. In case of the epoxy composite, there is a large delamination inside of the specimen, like this. But in case of the conductive polymer composite, so there is no internal damage found. There is a slight deterioration area is observed, but this is only the surface damages. So after that, we evaluate the residual strength. So in this case, we use the flexural strength test, like this. So in case of the CF epoxy composite, and after lightning test, the flexural strength decrease to the 24%. But in case of the conductive polymer composite, so for both cases, 40 kilomperes and 100 kilomperes, they remains 90% of the flexural strength of original strength. However, when we compare the intact strength for the CF conductive polymers and epoxy, so the original strength is much lower than the epoxy resins composite like this. Yeah, so the PANI CFRP had lower intact strength, but the strength degradation by lightning damage was very small. For the practical use, so improvement of the intact strength of the CF PANI is needed. Yeah. Okay. Well, this is my this slide concludes my today's talk. The first experimental and numerical approaches to elucidate the mechanism of the lightning damage of composite material was introduced. The numerical simulation predict lightning damage in good accuracy, but improving by incorporating physical phenomena that had not been considered is needed. A new material system with conductive polymer composite for lightning damage suppression was introduced. Now it is possible that the improvement in the conductivity in the out-of-plane direction is effective in regarding reducing the lightning damages. Thank you very much.